the thing I want to say is this isn't like a, this is our sort of one-stop solution for everything, but this is really the beginnings of a project, and also hopefully the beginnings of a kind of hopefully fairly lengthy series of engagement with different partners, of which, by being in the room, we, hope to engage with you as much as possible, involve you in the different aspects of this project, to collaborate, to try and, as William suggested, try to have some impact in the way that AI is adopted within, particularly the traffic control community. You can realize that over recent years, for example, there's been a sort of influx of companies such as the Ubers and things like this who have impact on transportation systems, but also have a large amount of intelligence going on as well, and are very adapted to AI techniques. Whereas what we're hoping to do with this project is to have the same sorts of technologies and enabling algorithms within, say, transport control, within a control center, within a civic authority, so that they can then adapt to a changing environment that is rapidly growing within artificial intelligence. Okay, but before I get into that in more detail, one thing I wanted to mention is the recent passing of Richard Gibbons, who was involved from this project from the very beginning. So some of you may know Richard Gibbons, some of you may not, but he, in much the way Ben Heydecker has been involved in giving us advice and academic advice in our project. Richard Gibbons was involved with this project from the very start. He was a reader at University of Cambridge, but as of this October would have been a full professor there, working on congestion control in all its various guises, from internet, telephony, to road transport. So Richard's been a great asset to this project, and it's a great loss, his recent and untimely passing. So I wanted to just make a note of that, as it was sort of the elephant in the room for many of us who are involved with this project. Okay. So, yes, I'll continue with the main parts of the talk now. So I want to give a sort of an overview of our sort of current vision for AI for urban mobility and the kind of project that we're getting involved with. So as was mentioned, it's a project at the Alan Turing Institute funded by the Toyota Mobility Foundation, okay, which is a charitable foundation which is looking to essentially improve mobility principles globally. Okay. Within this project, we have the following structure thus far, though it is something that will evolve over the initial period of this project. It's going to consist of Alan Wilson, who spoke at the beginning, who is the director of the Turing Institute and also the PI on this project. Within this, there are kind of two sub-projects, one with myself and Álvaro Cabrejas, okay, who's here at the back, and then Damon Wischik and a postdoc who we were interviewing for on Wednesday, okay? These two parts consist of looking into how artificial intelligence and more advanced reinforcement learning techniques can be used for traffic light signal control, okay? And the second part on systems of systems, so how can a local authority essentially incentivize the correct behavior from a much more diverse set of transport solutions, okay? So that might include Uber, it might include more flexible ride sharing, it might include the regular modes of transport, car, lorry, but also fleets, for example, delivery services, okay? So how does that liaise with a local authority which is trying to make efficiency savings across the whole system, okay? Now, within this, we've sort of placed this into a sort of umbrella where we're looking to kind of construct a software architecture. This is with Louise, who's here, and May, who is, I can't see, just at the back, so two opposite ends of the room. So Louise is a data scientist, and May is a software engineer, and we're looking to design essentially a system where we can link in various, let's say, database, live feeds, simulation softwares, so that we can then go about projecting and enabling transport planners in order to better deal with data sources, okay? So the idea there is something like going somewhere between AI, machine learning, which requires various coding skills, and, say, Excel, which is intuitive and usable to large numbers of people, okay? We want to have something that is sort of in the middle of that, where the domain-specific knowledge of a transport controller can best be utilized, okay? And then to enable them with various sets of data sources, resources, analysis tools, okay? So within this, we're looking to develop modern AI and data science tools for urban mobility, okay? To be able to explore data, generate and test different scenarios, okay? And then to optimize the performance of the system, both real-time or offline, okay? So as I've just said, so the AI for urban mobility, our aims, let's say for today, and our initial project is for, say, a year, but we're looking really to expand over a 10-year period, 5 to 10-year period, or engage with various parties and look to how we can better develop the utilization of AI within industry. Okay, so these are kind of more points for discussion throughout the day rather than me presenting solutions, but I would like us in the coffee breaks, which are always the best times, to have good sort of hearty chats with each other, not just us, but amongst yourselves about how AI and data science will change mobility systems, both now and in the longer term future. Okay. Our project explores this space with the aim of looking for impactful partnerships as well. Okay. So we want to discuss what are important lines of research that haven't been fully leveraged over in the transport domain, okay, directions of most impact and avenues of engagement, okay? So at some point or another, I imagine all of you we've reached out to at some different point, and we want to kind of keep those relationships going over a longer period of time, okay? And this is all with an eye to how we might expand this project beyond the initial setup that we have here. So there's an initial team, but like with Richard or with Ben, there is a broader set of network of people that the Turing brings together, and we can expand in appropriate directions, okay? So today, this talk and the other talks today are very much about utilizing that, okay? So now I'll go into a little bit more detail about the specific project that I'm involved in, which Alvaro's been working for about a couple of months on, so it's very early days, so it's not about presenting a final stop solution, but about the kind of techniques which we think are going to be useful, going to be deployed going forwards, okay, and investigating those, okay? After that, I'll pass over to Damon, who will then discuss the other parts of the project, okay? So we're looking into AI, artificial intelligence for urban traffic control, okay? So to quickly go over quick history, the first traffic light here was 1868, okay? It was manually controlled by a policeman and set fire to him at one point, at which point it was decommissioned, okay? Then, also in London, I think, St. James's Street, so not too far from here, was the first electric traffic light, okay? So not long after electricity is deployed, it's also deployed in traffic control, okay? Since the 80s and up until now, more or less, with various upgrades and all the rest of it, the Scoot system has been widely deployed within the UK, which is a vehicle-actuated control system, okay? So using loop detector sensors at different transport junctions, okay? One of the points I'm trying to make here is that at many points in time, the traffic control has been very much at the forefront of different technologies of that time, okay? So it might be the use of oil lamps, advent of electricity, better using of sensor data, okay? And with AI becoming more important, data science becomes more important, how do we then leverage those tools, okay? So next I'll just show a brief some results of Alvaro's project so far. Though this is sort of, so here we're looking into how you can use reinforcement learning algorithms in order to do traffic signal timing, okay? So we'll give a quick example, if I can get the slides to go, yeah? Oops. So here's how do I get this to play like this? So here's a quickly untrained traffic signal, okay? And what we're looking for, as we notice that we've got a long route over here with several aspects of cross traffic, okay? And we can see the untrained example experiences red cars, where red means waiting for 20 seconds or longer, okay? And then with, a few minutes or a minute or so of training, we can then get the algorithm to realize that actually it should be prioritizing the route over here in order to minimize congestion, get best throughput through the system, okay? And so in relatively short periods of time, you can optimize a system like this. And we're looking to essentially expand this out over much broader, wider areas, okay, for network control. So I talk about the kind of next steps with this, okay? So what are the kind of algorithms which are deployed here? Okay. Essentially, the state of the art in terms of learning, reinforcement learning, control, along the lines of this, which are implemented by DeepMind. Okay. The idea is that you write down a Markov decision process that you want to solve, an optimization you want to solve, and then you try to approximate the solution to that using something called a neural network. So here we've got a game of Space Invaders. We're essentially using a convolutional neural network to scan the space of pixels as to what color they are, and then from that, pass them to a neural network and then make a decision about what control action we should take. Okay? This is also something that's employed in the game of Go, like here. So we have various Go board configurations, and then we assess at each point the likelihood from that state of the optimal policy winning the game. Okay? And what we want to move from, without giving any maths and all the rest of it, is a solution where we're doing something similar in the same idea, but this is our simulation of the Melbourne urban area. Okay? So where we're looking at deep reinforcement learning algorithms for wide area control of large urban areas. Okay, so what do we need for this? We need essentially a simulation framework. Okay, so we're very happy to have people involvement with people like Immense.AI, PTV. We want to reach out to people like AimSum. Okay, we want to have an approximation architecture. So in our case, a neural network, and then an optimizer. So applying a certain gradient descent methods to optimize these, okay? And once we've set up a model, we've essentially got a playbook where we can then optimize the system. Okay, so our next steps will be, this is a map that Alvaro imported of the, where we are now, the British Library, King's Cross, Euston area, and how we then deploy this out over much wider areas, okay, in a distributed, responsive way that responds to incidents. Okay, and in doing this, we want to do this in a way that really engages with the different partners who are stakeholders in this sort of process. Okay? All right. At this point, I'll pass over to Damon. So this is one part of the project, but Damon is much more involved in the kind of system of systems. So rather than local optimization, the global aggregate demand response. Okay, thank you.
Thanks, Neil. Okay, second half of what we're doing, and as Neil said, this is very early days. It's aspirations and questions about whether you think this will work, how you think it should proceed, and how we can engage to make it successful. So we've been doing lots of running around, talking to many of you, talking to lots of people so far. Here's my understanding I've gathered from all of our many conversations. This is a picture of how data flows in the world of city planning and city operations today. Sensor networks widely deployed, control room screens. We've been delighted to visit control rooms at TfL and Transport for Greater Manchester. They're fantastic places. Live feeds, very extremely good infrastructure for getting data from here to the control rooms. And in some cases, all this live feeds to control rooms. The infrastructure is all set up, and great. It can be made accessible to the public APIs for looking at data. There seemed to me to be a barrier between what's there on the control room screens. This is the world of rich data versus the world of the operators. So the operators in control rooms, from what we were able to see, they work by experience. If you're someone who's operating the control room at one of these screens, you know what your city is meant to look like, you know what has happened in the past when you've seen problems, and you know what your standard responses are, but these are all in your head. They're not in a playbook, and they're not sitting there in a systematic body of data that can be interrogated. When it comes to planning, the typical flow of data from what we've seen is that there's this wonderful rich set of sensor data, and it's compressed into large aggregates, let's say origin-destination matrices averaged over a long time, and that is used as input to simulation software. Very often the simulation software, it's monolithic. There'll be a particular simulator for ambulances and a completely different simulator for the fire system, for example. There's no way to tie these together. So this is where this second half of the project wants to live. We want to ask, what are the data science bits that would help us tie together these pieces? The specific examples that we pulled from these situations. Let me just talk through one of these examples, then I'll explain why I think these are important problems. let's imagine we have a congested intersection somewhere in the city centre. Wonderful data feeds coming to the control room. The operator says, aha, there's serious congestion here. I'm going to adjust the timings of the lights upstream to reduce the traffic coming into this spot. There are buses up there. There are poor people on buses who then get diverted or delayed, and people think to themselves, oh, buses are crummy. I'm not going to take the bus. I'm going to take the car. And you end up with more congestion. The problem here, we have a world of bus system, highway system. If you try and optimize them independently, you will end up with bad outcomes. More abstractly speaking, a city is a network. It's an interconnected system made up of many subsystems, each doing its own thing. And a change in one spot can have unintended knock-on effects through the rest of the city. And the basic question we want to ask is, how can you detect these phenomena from your data? How can we make it really easy for operators to do that? I don't want it to be a job for people in universities or Turing institutes. I want it to be something doable by people on the ground. So as Neil said, we want to concretely build software. We're calling it Mobility Data Kit. We change the name every time, see what catches. Here's just a picture of what I think it might look like. You're sitting there. You load in a data set of, let's say for the sake of argument, I'm interested in the interplay between Uber and the public transport system. I've loaded in a data set of taxi trips. I've loaded in a data set of bus trips. It should be possible to drag them onto each other, and the system will do something cunning to build up a user model, data-driven user model, from which you will click and say, show me how one bit of the network interacts with another bit of the network. So essentially what I'm showing you here is what I think a operator's user interface might be for exactly the sort of sensitivity questions based on data that Ben Heydecker was talking about just this morning. Okay. So that's the overall goal of the project. There's a concrete problem of how can you use AI to improve traffic signal control. We're going to focus on a small number of concrete problems about knock-on effects in systems of subsystems. But our goal is to build a mobility data kit, a platform for handling data that is meant to generalize these and potentially many other problems. There are plenty of tools like Excel for handling and visualizing data. There are plenty of simulation pieces, which typically run as a batch mode. You configure it, you fire off your simulator. And there are plenty of machine learning pieces. Again, you have a program, custom-written program for doing a piece of machine learning. What we're really trying to investigate in this mobility data kit is, what would it look like? Is it possible to create a combined system, platform which lets you handle data but makes it easy to pull in bits of simulation as needed, bits of machine learning as needed, to gain understanding of the city as a whole? Okay, so that's a very quick overview of where we're heading with the project. Thank you.